Alright, so Merry Christmas. In this lecture, I'm gonna be talking about another important article on contrastive networks, and this is a technical paper because we are talking about different ways that we can do mini batch optimization. So I'm gonna talk about this particular paper in 2023, which is called Mini Batch Optimization of Contrastive Loss. The contrastive loss function ensures that embedding of positive sample pairs are similar while embedding of negative pairs are dissimilar. Practical constraints such as large memory requirement make it challenging to consider all possible positive and negative pairs, leading to the use of mini-batch optimization. In this paper, we investigate the theoretical aspects of mini-batch optimization in contrastive learning. We show that mini-batch optimization is equivalent to full batch optimization if and only if all B from n mini batches are selected, while suboptimality may arise when examining only a subset. And then we demonstrate that utilizing high-loss mini batches can speed up SGD convergence and propose a spectral clustering-based approach for identifying these high-loss mini batches. So we are given a data set of n positive pairs where xi and yi are two different views of the same object. And for the multimodal case, we can view x sub I and y sub I as two different modalities of the same image. For example, one of them is image, the other one is text description. So we consider contrastive learning where the goal is to find embedding vectors for xi and y sub I such that the embedding of positive pairs are similar, while ensuring that the embedding vectors of the negative pairs are well separated. So we define embedding matrices U and V, which are a collection of embedding vectors. Now we focus on simpler setting of directly optimizing the embedding vectors instead of model parameter theta and phi in order to gain theoretical insight into the learning embeddings. And this approach enables us to develop a deeper understanding of the underlying mechanism. So consider this, that for n pairs, we want to optimize embedding vectors. We want to minimize this contrastive loss of this U and V. And so it's just L2 norm. We set it to 1. And this is our constraint such that U sub I is equal to 1. Also V sub I is equal to 1. And the contrastive loss is just a full batch version of the loss which contrasts all embeddings with each other. Due to large computational complexity and memory requirements during optimization, practitioners often consider the following mini-batch version. It's a kind of technical trick. Note that there exists B out of n different mini-batches, each of which having B samples, and B sub k is the case mini-batch satisfying that this is inside n. And then the contrastive loss can be calculated. So there is a relationship between optimization of full batch and mini-batch. So we prove three main results. First, they derive in their paper, they derive the optimal solution that minimizes the full batch loss. and they show that the solution that minimizes the average of mini batch losses is identical to the one that minimizes full batch loss. And they show that minimizing the mini batch loss summed over only a strict subset can lead to suboptimal solution that does not minimize the full batch loss. So this is the definition of simplex ETF. ETF stands for this equiangular tight frame, and we call a set of n vectors form a simplex equiangular tight frame if first of all they are orthonormal, and second of all their dot product is this value -1 over n minus 1. So we say that a set of n vectors, for example, I varies from 1 to n, j varies from 1 to n. So if their dot product becomes this value, then they are both for all pairs, of course. Then we call it simplex equiangular tight frame. And they have a lemma that says, suppose n is less than d plus 1, and then the optimal solution of the full batch contrastive learning problem in the previous slide satisfies U star is V star, and the columns of U star form a simplex ETF. And there is another concept which is called symmetric and antipodal. So embedding matrices are called symmetric and antipodal if U and V satisfies. First of all, they should be symmetric. Then antipodal, it means that for each I there exists J such that this relation holds. And we conjecture that the optimal solutions for n equal to 2D are symmetric and antipodal. There is a different concept that they define here. Simplex cross polytope, because a set of n vectors form a simplex cross polytope if for all I the following three conditions hold. First of all, they're orthonormal. There exists first of all they are unit norm. The norm is 1. There exists a unique J such that the dot product is -1, and for if they are not the same, if this K is not in I and J, then their dot product is 0. So we call this simplex cross polytope. And now the main theorem says that U and V are symmetric, and if U and V are symmetric and antipodal, these two concepts that we explain, then the columns of U star form a simplex cross polytope. So the columns becomes cross polytope for n equal to D. So we go through the proof outline only. By antipodality assumption, we can apply this Jensen inequality to n-2 indices without itself and antipodal point. Then we show that the simplex cross polytope also minimizes this lower bound while satisfying the conditions that make the applications of Jensen's inequality tight. So you see, this is the full batch that you always use, but the mini batch could have many different combinations. For example, 3 and 4, 1 and 2. Or even all combination of mini batch. You can have many different combination of mini batches. And here in A, you see that how the loss of, for example, a full batch is different and the mini batch is different. Now, Here we consider the mini-batch contrastive loss optimization, where we first choose multiple mini-batches of size B and then find U and V that minimizes the sum of contrastive losses computed for chosen mini-batches. The mini-batch loss and full batch loss are not identical, nor is one a simple scaling of the other by a constant factor. In other words, there exists no constant C such that the loss of mini batch and the full batch are related to each other. So there is a proposition. And another important theorem is that the set of minimizers of the different combination of mini batch problem is the same as that of full batch problem for two cases, for this case and this case. And the pairs are restricted to those satisfying the conditions in definition 2. In such cases, the solutions satisfies the following: that first, U sub I forms a simplex ETF and Ui is equal to Vi. And for the second case, these vectors form a simplex cross polytope. If B is equal to 2 and n is less than d plus 1, then the minimizer of 4 for S is not minimizer of full batch optimization. Recall that the optimal embedding of the full batch optimization can be obtained by minimizing the sum of mini batch losses. An easy way of approximating the optimal embeddings is using gradient descent on sum of losses for B from n choose B mini batches, or to use a stochastic approach which applies gradient descent on the loss for a randomly chosen mini batch. Recent works found that applying gradient descent on selective batches outperforms SGD in some cases. So the natural question arises, does this hold for mini batch contrastive learning? Specifically, the question is SGD, is stochastic gradient descent enough to guarantee good convergence and mini batch contrastive learning? And the second question, can we come up with a batch selection method that outperforms vanilla SGD that everyone uses? So we show that ordered SGD can potentially accelerate convergence compared to vanilla SGD in a demonstrative toy example. We also show that the convergence results from Kawaguchi can be extended to mini-batch contrastive loss optimization. Then they reformulate the batch selection problem into min-cut problem that I've explained in a playlist for approximation algorithm in graph theory. So by considering a graph with n nodes where each node is each positive pair and each edge represents a proxy to contrastive loss between two nodes. This allows us to devise an efficient batch selection algorithm by leveraging spectral clustering. So this is a theorem says this is a lemma says contrastive loss is a geodesic non-quasi-convex function of U and V on T. So the main algorithm, first we get some number of positive pairs, batch size B, we fix batch size B, and then we have embedding matrices U and V. And the output of this algorithm is just selected batches. How does it select these batches? So first we construct the affinity matrix. In graph theory, you should be aware of affinity theory. degree matrix and the kind of Laplacian. So I assume you all know. And then we apply even size spectral clustering. I've explained spectral clustering in that playlist as well. And then you return those batches. So you understand how to deal with these mini batches, how to select the batches.